Hi, thanks for joining me. Today I'm going to be going over problem 1 from week 8 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be tackling today, and it's kind of a geometry problem. We say that a tiling of a convex polygon P is a set of regular polygons which are not necessarily the same, such that no two of these polygons overlap, and overlap other than maybe at edges or vertices. So if you have a convex polygon, say, I don't know, this guy here, like that. So convex just basically means within the shape, you can draw a straight line from any 2 points that are in the shape. So for example, here to here, they're both points within the shape, and I can draw a straight line, and that straight line remains within the shape. But for example, if I draw a star of sorts, something like that, this is not convex, because if I draw those 2 points, the line in between them does not remain within the star. So this is convex, this is not convex. Anyway, and we say that a tiling is basically when we can fill this guy up with regular polygons. So perhaps we could do this. So that guy there, say, is an equilateral triangle. Maybe this thing here. So that's an equilateral triangle, and so on, until we kind of fill this shape up here just using regular shapes. So we could perhaps introduce a rectangle like that or something like that, and continue until we've only got regular shapes involved, and that would be what's known as a tiling. This, as it is not a tiling, because clearly this shape here is not regular. It's a triangle, but it's clearly not an equilateral triangle. But of course, for example, if you took, say, a rectangle like this, one way you can make a regular tiling of it is, say this length is 2a, and this length is a, then you can just draw a straight line through the middle, and now you've got two essentially equilateral foregons, so equilateral squares, or just squares, and their union equals the rectangle that we started off with. And these two squares only ever overlap at the boundary, at the edge. So I can't have, say, one square like this, and then one square kind of overlapping, and then one like this. But yeah, hopefully you get the picture. This is what we're going to define a tiling to be. So essentially, these regular polygons going into a convex polygon in such a way that they don't overlap, and they exactly fill our start polygon P. We want to find all polygons P, all convex polygons P, where the number of tilings of P is a finite positive integer. So there exists certainly at least one tiling of the convex polygon P, but there are only finitely many. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the first thing I do is I claim that if we have a solution to our problem P, so P is a convex polygon and it has at least one tiling, and also the number of tilings is a finite positive integer, then P cannot contain, or any tiling of P cannot contain an equilateral triangle, a square, a regular hexagon, or a regular 12-sided shape, which I believe is called a dodecagram. Okay, and the way to see that is if it did contain, say, a regular triangle, so an equilateral triangle, like so. So this is part of its tiling, and then it might have some other shapes. It might have a square. Imagine this square coming across like that, and some other things, and we get P. But the thing we're focusing on is the equilateral triangle. If it contained an equilateral triangle, or then we can do something to get another tiling. We can just split this equilateral triangle up like so. So we divide this guy here by half, draw on this line, and all of a sudden we've taken our equilateral triangle and drawn it as 4 more equilateral triangles, so we've generated another tiling. But then we can repeat the process now with this equilateral triangle. We can split this up, like so, and now we've got another tiling, and we can keep doing this an arbitrarily large number of times, and that will give us an infinite number of tilings of P, which contradicts the fact that P is a solution to our problem. So that's the case where we have an equilateral triangle. You can do a very similar thing for a square. So if your tiling contains a square, well, you can split it up like this to get another tiling, and that is also 4 squares, and do it again, say on this kind of window, and again, and so on, an arbitrarily large amount of times. For a hexagon, you start off with your hexagon looking something like this. Okay, and then what you do is you put your center on, and you're going to make 6 equilateral triangles, so kind of like slices of a pizza, a hexagonal pizza, like so. Okay, and again, once you've got these equilateral triangles, you can then do this thing here and get an arbitrarily large number of tilings. And I'll leave the case where you've got a 12-sided polygon as a little exercise to use. So show how you can kind of split up your 12-sided polygon in a way to generate an infinite number of tilings. Anyway, let me clean up the whiteboard and we'll continue. Okay, so the next thing I want to do is make a claim and then prove that claim. And that claim is if P is a solution to our problem, so P is a convex polygon, it has at least one tiling but only a finite number of tilings, then, and we have C being a tiling of P, then any vertex of C must also be a vertex of P. So if, say, our polygon P was, I don't know, this guy here, this was our convex polygon, and let's say that we had a tiling C, and let's say one of the kind of regular n-gons on C was, say, this guy here. Okay, then I claim that this actually won't lead to a tiling because we can see here we've got a vertex on what I claim is our tiling, but this vertex is not a vertex of P, so I claim that this won't work. And in fact, this wouldn't work anyway because what we've got here is an equilateral triangle, and by the argument I just had, we can't have any equilateral triangles on our diagram. Okay, so the way we're going to prove this is by contradiction. So we're going to suppose for contradiction there exists a tiling of P with at least one of the vertices of C not being a vertex of P. Okay, so then what we're going to do is let S be that set of vertices, and we're going to assume that S is non-empty. So S is going to be defined to be equal to the set of vertices V of C. So V, let's say, is a vertex of C, but V is not a vertex of P, like so. So something like this, and we're assuming for contradiction that S is non-empty. Well, firstly, notice that if V is in this set here, then either V is on the boundary of P, so it's like kind of on the perimeter, but not on a vertex, or V is on the kind of interior of P, so they're kind of two different cases. Anyway, what we're going to do is consider the convex hull of our set S. So if you haven't heard of what a convex hull is before, don't worry, I'll kind of give a brief explanation now. If we have, say, a set of points on our plane, say these guys here, let's say that thing there, the convex hull of this set of points is simply the smallest, I guess, convex polygon which kind of encapsulates all these points here. So so it's the smallest convex polygon on the plane, which has each of these points here either in that polygon or on the boundary. Okay, and we define smallest to be one with a minimal perimeter. Okay, so firstly, the convex hull exists, and also another property of the convex hull is that if you take a vertex on, out of these points here, at least one of those points must be on the vertex of your convex hull. Otherwise, you can make the perimeter smaller. Okay, anyway, we have this thing here. So in this case, if this was our set S, the convex hull of S would probably be something like, would look something like this maybe. And you can see that all the points are either on the boundary of S or on the inside. Okay, and each point is, there's at least one point which is a vertex. So say this guy here. Anyway, what we're going to do is take our convex hull, the convex hull of this guy here, this set S here, and we're going to take a vertex V, which is in S, and also on kind of it is a vertex of the convex hull of S. So V is in S, but V is also a vertex, I guess, of convex hull of S. Okay, so we're going to take one of these vertices here. And now what we're going to do is look at all the adjacent polygons in our tiling. So remember, we have our polygon P, which say looks something like that. Okay, so this is P on the outside. And then we have some sort of tiling, which I'm not going to kind of draw on, but then we're going to have this convex hull S. So let's say this is our convex hull. I'm not sure, let's say that's our convex hull. Okay, and then let's say that this here is our vertex V. Then what we're going to do is look at all the adjacent kind of polygons that are in our tiling. So say if we look at all the polygons in our tiling that are adjacent to this vertex here. So maybe you have this guy here and that has angle θ1, this one here θ2, and this one here θ3. So in this case there are 3, but what we know is because that's a straight line, θ1 plus θ2 plus θ3 equals pi. But I guess more generally, we can just do the sum up to k, because of course in the case I've drawn we've only got 3 kind of adjacent polygons, but obviously in general it would be theta 1 plus theta 2 plus so on all the way up to theta k, and that equals pi. But that's in the case where the vertex is kind of on the boundary of P. And the other case is if we have, say, V being in the middle, so in the interior. In which case, when we kind of look at that and look at all the, in our tiling here of C, we look at all the other, say, adjacent polygons. Say we've got something like this, I don't know, something like that, say. Okay, but basically all these angles here are going to add up to 360 degrees, so 2 pi. So if this is theta 1, theta 2, theta 3, and so on up to theta 4, and so on. So theta 1 plus all the way up to theta k is 2 pi. So in other words, when I add up these theta 1 all the way up to theta k, it's either going to be equal to pi or 2 pi, depending on whether V is on the edge, kind of on the boundary, or if it's on the interior. And I claim that both of these guys here are impossible. And the way we're going to do that is use the fact that each of these theta i's are interior angles of a regular polygon. Anyway, let me clear up the whiteboard and I'll prove that both of these cases are impossible. Okay, so I've written down a fact, and that is that theta equals pi minus 2 pi over n. So what I mean by this is if you take a regular n-gon, then the interior angle will be pi minus 2 pi over n. And I'm not going to prove this fact in this video, it's kind of a common fact, but if you want to experiment with like n equals 3, n equals 4, and so on, and you'll see that this fact is indeed true. Anyway, what I do is, what I've written down, sorry, is a claim that I had up just a second ago, and that is when you sum up these kind of angles, theta 1 up to theta k, it can never be equal to pi or 2 pi, from what we had before. So we're kind of continuing the proof from before, and the first thing we're going to do is show that it can never be equal to pi. And I guess one way to see that is first you notice that each of these theta i's, they're going to correspond to angles of n-gons, but those n-gons, remember n can't be equal to 3, 4, 6, or 12, because we kind of covered those cases, and in the claim that I had on the previous whiteboard, we assumed that P was a valid solution, so that meant that P couldn't contain any 3 gons, 4 gons, 6 gons, or 12 gons. Okay, so that in particular means, because we know normally for an n-gon we have to have n at least 3, but because we're assuming n is not 3 or 4, we must have that n, I guess I'm going to denote it ni, is going to be bigger than or equal to 5. Okay, so these theta i's kind of correspond to the regular ni gons. So in particular, then that means that theta I is going to be equal to pi plus 2 pi over ni. So where ni is just essentially the ni gon that is associated with this angle here. Oh, sorry, minus that's supposed to be. But because ni is at least 5, this guy here is going to be at least pi minus 2 pi over 5, and that guy there is 3 pi over 5. But then if we come back to this thing here, suppose we had theta 1 plus dot 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 all the way up to theta k was equal to pi, like so, so we'd have this thing here. But then we notice that this thing here is at least k times 3 pi over 5, because we know each of these theta i's are going to be at least 3 pi over 5 from this angle, from this argument here. And of course there are k of them, so this thing here is going to be at least k times 3 pi over 5. But notice that if k is, sorry, this thing here, yeah, this thing here is going to be at least k times 3 pi over 5. But notice that if k was bigger than or equal to 2, then this thing here would be bigger than or equal to 6 pi over 5. And then we get that pi is bigger than or equal to 6 pi over 5, which is definitely not true. So that must mean that k is strictly less than 2. So in other words, k equals 1. But remember what this kind of setup means. This is kind of corresponding to our vertex V, which is in our convex hull, and also kind of on the edge of the, sorry, it's one of our vertices of C, and it's on the edge of P, but not a vertex. So that means that you can't really have only one adjacent polygon, because it's a vertex on a boundary. So if it's a vertex, there's got to be some polygons associated to it. So you can't have k equals 1, it's got to be at least like k equals 2, for example. So yeah, this leads to a contradiction. We can't have k equals 1. So that deals with the case theta 1 plus theta k, theta 1 plus all the way up to theta k not being equal to pi. Now we're going to show using a similar argument that it can't be equal to 2 pi as well. Okay, so now I want to prove that theta 1 plus theta 2 plus so on all the way up to theta k cannot be equal to 2 pi. And I've kind of rewritten the theta i's as what I had before from the fact theta I equals pi minus 2 pi over ni. So we want to show that this sum here cannot equal 2 pi. And the way we're going to do that is by contradiction. So suppose for contradiction we could achieve this thing here for some k and some ni's. Well, what we're going to do is firstly use a similar technique to what we had before. So we showed that this guy here, each of the theta i's, is bigger than or equal to 3 pi over 5. But also remember this guy here, which of course is just theta I, this thing here is very clearly less than pi, because it's pi minus some positive quantity. So if we look at this thing here is equal to this guy here, the sum from I equals 1 to k of pi minus 2 pi ni. And of course this thing here, while it's lower bound, we know that each of these guys here are bigger than or equal to 3 pi over 5, so we know this is going to be bigger than or equal to k times 3 pi over 5. But what's its maximum? Well, each of these guys here have maximum pi, so its maximum thing here is going to be k pi, like so. So we need this thing here, this thing is always going to be in that interval there, but we want that thing there to be 2 pi. So we need 2 pi to fall inside that interval. So we need 2 pi to be less than k pi, which of course gives us that k is bigger than 2. Okay, so k must be bigger than 2, but we also need 2 pi to be bigger than or equal to that guy there. So 2 pi is bigger than or equal to k times 3 pi over 5, and just rearranging this, cancelling the pi's, and then bringing the 5 and the 3 onto this side, we get that k is less than or equal to 10 over 3. But of course k is an integer, so this thing here means that k is less than or equal to 3. So k is bigger than 2 and k is less than or equal to 3. Clearly the only integer that satisfies that is k equals 3. So if we are ever going to have a contradiction to this inequality here, so in other words, if there exists some ni's and some k's, such that this left hand side equals 2 pi, we must have that k equals 3. But I claim that that is also impossible as well. Anyway, let me clean up the whiteboard and I'll prove that k equals 3 is impossible. Okay, so suppose the sum from I equals 1 to 3 of pi minus 2 pi over ni equals 2 pi. So I've just replaced k with 3 here. So then we can just kind of expand this out and we're going to get 3 pi minus 2 pi 1 over n1 plus 1 over n2 plus 1 over n3. This guy here equals 2 pi. And then if you just go ahead and rearrange this, so bring this whole thing onto that side, 2 pi onto this side, and divide through by pi's and stuff, you're going to get that this whole quantity here is just equal to a half, like so. So we have 1 over n1 plus 1 over n2 plus 1 over n3 equals a half. Now remember, these ni's are just like the number of sides of the n-gons. They are the n-gons that surround the vertex v. So firstly, we can assume without loss of generality that these are kind of in increasing order. So n1 is less than or equal to n2 is less than or equal to n3. But then of course that means that 1 over n1 is bigger than or equal to 1 over n2 is bigger than or equal to 1 over n3. So then that means that 1 over n1 plus 1 over n2 plus 1 over n3, 1 over n2 plus 1 over n3, this guy here is going to be less than or equal to 1 over n1 plus 1 over n1 plus 1 over n1, which of course is just 3 over n1. But we know that 1 over n1 plus 1 over n2 plus 1 over n3, we know that's just a half. So we get that a half is less than or equal to 3 over n1. So rearranging this gives us that n1 must be less than or equal to 6. Okay, so just rearranging a half is less than or equal to 3 over n1 gives us that n1 is less than or equal to 6. Remember, n1 can't be equal to 3, 4, 6, or 12. So in fact, this implies that n1 simply must be 5. Okay, then we can plug that back into this guy here and apply a similar argument on n2 and n3, and we'll get that n1, n2, n3 must be 5, 5, 10, like so. Okay, so you can just go ahead and check that for yourself, but this is the only solution to this guy here. But I claim that this is impossible. So a lot of it is, I claim that this is impossible, but the only time it could potentially fail is this case. This case is impossible because the only time it could potentially fail is this case. Now finally, I claim that this thing here is impossible, and I'm just going to kind of prove that by a diagram. Let me clean up the whiteboard and I'll prove that this is impossible. Okay, so I claim the 5, 5, 10 case doesn't actually work, and I've kind of drawn it up here. Here's my pentagon, pentagon, and my tengon here. I haven't drawn the whole of the tengon, I've just kind of drawn the bottom half of it. And of course this is our vertex V, where they all kind of meet. Now the thing to remember is that V was supposed to be on the convex hull. Sorry, it's supposed to be a vertex of our convex hull, and I claim that this isn't possible. And the reason we kind of know that is, remember, our polygon P is convex. Now that means that this can't be the boundary of P. And we know that because if that was the boundary of P, then those 2 points, I can't draw a straight line between them. Okay, so then that means that there must kind of be some more regular polygons to the left of this kind of line, and then P is kind of surrounding it. But in particular, that means that this guy here is a vertex of C, vertex of our tiling, and it's in the interior of P, so it would also be in the set S. And then similarly this guy here. Okay, and equally this guy here as well. So now these three guys here are in the convex hull of, sorry, those three guys there are in S, so in particular they must be in the convex hull of S, but there's no way that this guy here can be a boundary, can be a vertex of a convex shape that includes all three of these guys here. Okay, and you can probably just have a play around with that and see why that's true, but any convex shape that has these 3 points in, there's no way that can be a vertex of, because, you know, you can maybe have this as a vertex for these 2 points, like so, but then you can't have that guy there, because if you tried to, you'd have to have a shape something like this, but this clearly isn't convex, you know, by drawing that line on there. So the 5, 5, 10 case doesn't work, and that proves my claim, and that is that if we take a solution P, then we take a tiling on it C, any vertex on that tiling must also be a vertex of P. So it's kind of a long lemma, I guess, if you want, but that lemma is going to be very useful in just a second to wrap up our problem. Okay, so to keep this video relatively short, and also because I'm a little lazy, I'm not going to give you the end to this solution. I'm going to leave it as a bit of homework, but I've written out a few bullet points which should hopefully not give it away, but essentially work through these bullet points and you'll be able to solve the rest of the problem yourself. So the first bullet point is that P must be a regular n-gon. So this is kind of, if we just look at the proof we just had, where we proved that any vertex of a tiling C must be a vertex of P. And then what we can do is, well, notice straight away that because each angle of the regular n-gons in our tiling must be at least 3 pi over 5 from the argument we had, then we can't have two angles at the same vertex, because then, you know, 3 pi over 5 plus 3 pi over 5 is 6 pi over 5, which is bigger than pi. So then that means that that angle at that vertex there, the angle is bigger than 180 degrees, and then of course that can't be a convex polygon. So that kind of proves the first claim, or at least it gives you a sketch proof of it, but you can go through that rigorously and prove that P must be a regular n-gon. And of course we know that n can't be equal to 3, 4, 6 or 12 from the arguments we had before, but I claim that all other n work with only the trivial tiling. So if you take an n-gon where n is not 3, 4, 6 or 12, then the regular n-gon of course has the trivial tiling where you just place that n-gon on itself, and I claim that that's the only tiling for that n-gon. And the way you can prove that is by contradiction. So suppose that there are two tilings, and then again look at an angle, and then do some computations on the two different sets of tilings on that angle, and essentially you're going to get them down to one case, and then that case you can also prove that is impossible. So kind of like what we did before. So this will prove that the only solutions to our problem is, i.e. the only convex polygons which have at least one tiling but a finite number are simply the regular n-gons for n at least 3, but n not equal to 3, 4, 6 or 12. And that will solve our problem. So I guess perhaps not the most satisfying end to this video, but I think it is always nice to, you know, not give everything away and give yourself a challenge to really make sure you've understood everything I've said so far. But yeah, if you do have want any more pointers on this, do have a play with it, and if you do want any pointers, I'll perhaps leave some hints in the description, maybe after a day or two if people are really struggling. But yeah, I'll leave this video here. Thank you for watching. I'll catch you in the next one. Have a great day.